Previously, we have defined what is optimization, and we have seen one example of optimization problem important in engineering. Now in this lecture, we'll talk about one-dimensional unconstrained optimization. We'll look at the definition as well as example of one-dimensional unconstrained optimization. We'll look at how we solve such problems analytically, and then we'll take up a very simple technique that is known as random source technique for numerically solving one-dimensional unconstrained optimization. So first let us see what is one-dimensional unconstrained optimization. Unconstrained optimization, as you already know, that optimization problem where there is no constraint. And in reality, it happens more than what you can think of. In many cases, of course, you will find that the role of constraint is minimal because constraints are set in a way that the solution of real problem doesn't reach there. So they can be modeled as one-dimensional or multidimensional unconstrained problem. Similarly, in many multidimensional unconstrained problem, you will see that they can be reduced to a series of one-dimensional unconstrained problem. So let us first see what we are talking about. So our goal is to minimize a function y f of x, and in general this x is a vector. Mathematically, when we write that minimum of x in fx. That means the x that minimizes fx. This x is in an n-dimensional real space, and these are the only constraint we will bring in unconstrained optimization, that the variables we are talking about, they are real variables. X is a vector and it could be in general an n-dimensional vector. So x is in Rn, that is n-dimensional real space, and f is a function that takes an input from Rn, such as this x, an n-dimensional input, and then it gives an output that is in real space R, which is y in this case. Input is x vector and output is y. So for a real vector x and a real scalar y, the global minimizer, that is x star, that is the value of x which will minimize fx for all x. This sign of inverted a means for all, so there is no need to get intimidated with this. These are just symbols which help us to write briefly. So for all x, if we find a value x star is given by this x which will minimize fx, then we hit the global minimizer x star. Similarly, local minimizer x star does the same thing, but not for all x. This is for x which is in a neighborhood of this point x star. That neighborhood could be anything that you can define. In any case, this is global or local, this f of x star must be less than or equal to f of x. In case of global, this x can be anywhere. In case of local, this x will be within the neighborhood. Now, a special case of such optimization, this is what we have defined now. This is unconstrained optimization because we didn't talk about the constraints at all here, other than the fact that they are in real space x and y. Now we come to this special case where x and y both are in one-dimensional real space. So both are scalar, and f is a function that will take scalar and give a scalar. We only talk about this. So it can't go any simpler than this. So we have removed the constraints from optimization problem, and then instead of taking a general vector as input, I am taking a scalar as input. So I have scalar input, scalar output, and no constraint. So you cannot have anything simpler optimization problem than this. And this is where we'll spend some time, we'll talk about it. You will see that even though it's a very simple problem, we can learn a lot by solving this problem. These are the problem we call one-dimensional unconstrained optimization. This is unconstrained because there is no constraint. This is one-dimensional because this x is one-dimensional vector, or x is a scalar. This is also known as single variable unconstrained optimization. This single variable is once again that is x. That is the only variable that we are concerned with. So now let us take an example. So let us take the fuel economy of an automobile, and we define fuel economy is that in using 1 liter fuel, how far the automobile can go. If I do experiments in it, then I get this red dot. These are the points. Here in x-axis, I have the speed of automobile, and y-axis, I have this fuel economy. So you can see that with speed, the fuel economy first increases and then it decreases. Now, if we fit a regression model over these discrete points, then I get a smooth curve, this y equals f of x, ax cube plus bx square plus cx plus d, and this curve you see as this blue line over here. This a, b, c, d are constants, and we all know that how to find them from regression. So using regression, we have found such values for a, b, c, and d. Now in such a problem, the goal is not really minimization. As such, we wish that the fx is maximized. Fx means this is our y here. That should maximize. Now fx is a one-dimensional function. One-dimensional in the sense that the only independent variable here is x, which is a scalar. And this one-dimensional function, its minimization or maximization, there is a theory in calculus. I believe all of you know that theory, but let us spend a moment on that. So for such one-dimensional function fx, if f prime x at certain point x star is 0, then this point x equals x star, we call it a stationary point. Now a stationary point could be minima, could be maxima, and it may not be minima or maxima, it could be a saddle point, but let's not get into all this detail. It is sufficient just to remember that x equal to x star will be a maxima if f double prime x at that location is negative, and it will be a minima if f double prime x at that particular location is positive. Proof of this is excluded. This is not necessary for this course. You can go back to any standard calculus text. Undergraduate calculus text is sufficient to look at the proof. So if you don't remember this, this is a good time that you go and revise some of these basic concepts from a standard calculus text. Now, since this theory here is available, we can simply use them to find the maxima in this case we are looking for this y equals fx. So what we do here is that we know this y equals fx, and we need to calculate the derivatives twice actually for this function. So we find the derivative f prime x is that 3ax square, because I had this ax cube here, 3 comes here, 3ax square plus twice bx plus c, and d is a constant, so it doesn't appear here. So 3ax square plus twice bx plus c, and in f double prime x, it is 6 times ax plus twice b. From here, I take the derivative, 2 comes here, so 6ax. Now, f prime x equals 0, that will give us the solution here using the standard solution technique of quadratic equation. I get this minus b plus minus root over b square minus 3ac by 3a, etc., etc. And then I calculate from this ABC values, and I get this f prime x equals 0. It will be 0 at 2 points. One is this 65.625 and another is 169.444. So f prime x at 65.625 is 0. If I check this f double prime now, it gives me negative at 65.625 and it gives me positive at 169. Now you see that we are not interested about 169 at all. We are only looking in this range roughly between 0 to 100. So one thing we can say that here this is negative, means at this point it will maximize, and at 169 it will minimize. But 169 is not an important point for us. This is beyond the study domain. So what we do is that we focus only on this 65.625, and that tells me that the maximum value of y will be given by whatever its value come at x equals 65.625. So somewhere, let us say around this point, it will hit the maximum here, and that is slightly less than 20. That comes as 18.58. So that is the maximum value of y, and it gets its maximum at 65.625. So this x star is 65.625, where the function gets its maximum. Now this was a simple problem, but we cannot expect this to happen all the time. So in general, what happens, this f dot x equals 0 will not have an analytical solution. We cannot expect to have an analytical solution all the time. Depending upon the nature of this function that we are minimizing or maximizing, this f prime x could be very difficult to solve. So in general, what we do is that we have to use a root finding technique that we have discussed before to solve this f prime x equals 0. So for example, Newton-Raphson or bisection type method we have discussed before. So that kind of method can be used to solve f prime x. Therefore, one-dimensional unconstrained optimization problem, it may be converted essentially into a root finding problem. And we have already discussed root finding technique, so there is no need to discuss any new technique in this regard. So this is the first way of solving one-dimensional unconstrained problem, by root finding. But then let us try a different thing. Let us try a numerical approach, that is random search. That would be our starting point. So what is random search? Well, random search is a very simple technique. What it does is that within the domain of our interest, we randomly select x, and then at that x location we check the value of y. If I get a higher y than what was it before, I take this higher y as my current value, and I keep on doing this for as many random numbers as possible. So eventually I'll hit the highest point. That is the idea. So it's a very simplistic idea. So my selection of x and then comparing the value of y equals fx between different x. If the number of x are sufficiently large, then I'll pretty much cover all the points in this domain I hope to cover. Then I'll eventually capture the maximum or minimum. This is of course a very much, you understand, this is a brute force type method. But the good thing about it that not always functions will have well behaved like this blue line. Function may have many optimas, many maximum minimas, this kind of bad functions for optimization. And many traditional methods will fail there. In such cases, random search or similar kind of optimization algorithm could be very helpful to find the global optimum, global minimum or global maximum here, when there are so many local minimas and maximas, they appear in the function. The computational cost will be pretty high depending on the domain size. You may have millions of trials you have to see. But then it doesn't have any other constraint. It could be any type of function. The function may not be even continuous or differentiable for applying this technique. You will see later on we'll discuss many elegant technique, but then we have to differentiate and then sometimes double differentiate the function. But here we do not have that kind of requirement. This type of technique we call meta-heuristic technique, and this is a big universe in optimization. This is of course the basic minimum of a meta-heuristic technique. It can't go any simpler than that. But we can improve this technique quite a bit, and this kind of meta-heuristic technique are used heavily in optimization problem, especially for complex optimization problems where we have many minimas and maximas within the domain of our interest. So let us now see here how we will actually apply this algorithm in finding the maximum of this function. So here we have a Python program. You can just write this program in your Jupyter notebook or any other Python editor, or you can go online and find Python editor, Google Colab, etc. You will get exactly the same result, more or less exactly, because this is random. So there may be slight difference. So here I start with number of trials here. This many random numbers I'll generate and I'll check where the maximum comes. And these a, b, c, d's are constants, and I define this function f as this ax cube plus bx square, etc., etc. Now I define the domain of my interest that goes between 10 to 100. Within this, I'll look for the maximum. And this is actually the size of the domain, x2 minus x1. To get my function, I'll get this f, that is my lambda function, and a value, if I give an input to f, it will calculate, it will take that input, treat it as x, it will calculate and it will give me back. So this is the way I can calculate the function. Now I go in this for loop and I continuously generate random number. Every random number I generate, it by default, it will generate between 0 and 1. I make sure that that is being generated within this x1 and x2. So I take this point x3 where the random number is generated, that is x1 plus L multiplied by this random number, and this makes the random number, which this random number is generated between 0 and 1. Now this x1 plus L multiplied by this, it will scale it within x1 to x2. Then I calculate the f3 here. That means the value of my function as x3, and then I check if my f3 is greater than f2. f2 I have calculated before, that is the value of f at x1. If f3 is indeed greater than f2, then I assume that this is my maximum. So I take that as my x star, that is x3, and my y star is f3. They are my maximum. And then I store this f3 value in f2. And now I repeat it once again, my f2, new f2, now this. As soon as I get an f3 that is greater than this f2, I'll take that as my new maximum, and I'll keep on doing this over and over for n number of times. And n I have to keep a large number, otherwise there is no chance of getting a good result. If you run this program, you will find that, at least what I have found, I ran this program and I found that it is coming at 18.58. You may have slightly different results based on the number of trials, or even if you run with same number, if you run this program twice, you can get a slightly different result because it depends on the randomness. So there is a stochasticity in this particular way of problem solving. But those difference will come probably after a lot of digits after the decimal. So 18.58 more or less you will get no matter what. So that tells us that it's a very simple technique. You really don't need any elegant mathematics here. But this simple techniques gives us same result as the analytical. Of course, in this case, the analytical solution is also simple. There is nothing really serious about it. You may wonder that why I'm going to write a program when analytical solution is simple. But this is only to give you an example. You can use this when analytical solution is slightly difficult. The program, of course, this is the very basic program. As I said, you can improve this further. You can change the number of trials automatically and see that what are the differences it is giving. And in that way, you can minimize the number of trials here. Your program will be faster. Now we come to this very interesting aspect of optimization problem. We have already discussed that optimization problems are sometimes reduced to root finding problems, one-day unconstrained optimization. Well, the reverse is also true. This is very interesting. We have learned root finding techniques such as Newton-Raphson, but then root finding can be accomplished using optimization technique. So how? So let us see. So for example, let us say that we have a function y equals fx, and it has one and only one root in this interval x1, x2. So at that particular point x star, I have this equals 0. So therefore, I can say that this x star point, it will minimize this function phi x if phi x is square of this fx, or phi x is the absolute value of this fx. And you can define many different phi x actually. If phi x is the integration of fx, then also you can do so. So let us see an example. So let us say that we want to evaluate root 2, and you have already evaluated root 2 using root finding technique. So let us see that if we can do so using optimization technique. To evaluate root 2 from root finding, what you did is that you have solved this equation x square minus 2 equals 0. The solution of this equation will give you the value of root 2. Now you see that this is the equation x square minus 2. This blue curve cuts the x-axis over here, and this should be the value of root 2. You can see clearly it is coming near 1.4. So this is the value of root 2. Now what I do, I take a new function phi x, that is x square minus 2 whole square. That means that this is the square of fx. If I now plot this, this comes as this blue line. What you see that this fx function was 0 only at this point. So when I square that, the 0 will remain 0. But both the negative part and the positive part of the fx function, they will now be positive because I have squared them up. So everything in this blue function is positive except there is one point where it is 0, which means that at this root 2, this particular point, this phi x function will get its minimum. So instead of finding the root of fx equals x square minus 2, we can find the minimum of phi x equals x square minus 2 whole square, and the point at which this function will minimize, that will give us the root of x square minus 2 equals 0. So now x square minus 2 equals 0, you can find it using Newton-Raphson. But this problem of minimizing this x square minus 2 whole square, we can find using this standard random search program that you have already created. You can see between the last example and this one, the only difference is that now I have a new function x square minus 2 whole square. Because in previous case we were maximizing. If you want to maximize here, you can put a minus sign here, but I am not maximizing. I am just changed here this greater than to less than, and that will minimize this function. So other than that, it's all same. I have taken an interval for search between 0 to 2. I hope that within this interval, I'll get the minimum of this function. So this is my 0 and this is my 2. Clearly the minimum is between them. And L is once again the interval x2 minus x1, and f2 is f at x1. Then I go in the for loop and I calculate this x3 by generating this random number and then scaling the random number between x1 and x2. So this my random number gives me this random location x3, and I find the value of this function f at that random location. Now I come in this loop. If f3 is less than f2, it is not greater than anymore because I am minimizing now. If f3 is less, then I say that, well, this is my minimum. So I put my x star, y star there at 0.3, and then I put this value, store this value as f2. I keep on doing this for large number of trials, and eventually I hope that I'll get the minimum of this function, which will be the root of this x square minus 2 equals 0. That means which will be the value of square root of 2. Now I actually ran this program, and this program gives an output of 1.414. That is the value of x star where the function will minimize, and this 3 into 10 raised to minus 11, it gives the minimum value of the function. That is the value of the function here. That means this is the y star. So you can see that this is very close to 0. This is what we have expected because everywhere else it is positive. So this is where it is basically hitting 0 at 1.414. So this is the value of root 2. So therefore, you now see a new method of finding the value of root 2 using optimization technique and a very simple numerical technique for optimization. Earlier you have obtained it from root finding using Newton-Raphson bisection type method. But now you can see that without going through that, this is actually a much simpler technique to find the root. So now we are ready to summarize. We have seen one-dimensional unconstrained optimization problem. In general, they can be reduced to a root finding problem, and then we can use root finding techniques that we have learned before. Similarly, root finding problems may also be formulated as optimization problems. Now here we have discussed only with a very trivial case, but many modern linear solvers, Ax equals b solvers, they use this philosophy, and instead of solving Ax equals b directly, they find a function for which the minimum point will be the solution of Ax equals b. That creates this method. For example, conjugate gradient method, you may have heard the name. Conjugate gradient method solves Ax equals b exactly this way. It solves a function for which the derivative is Ax minus b, and then it gives the solution back from optimization, the solution of Ax equals b. We have also seen a random search method. This is a very easy to implement, a meta-heuristic method. So this is a common sense random number based method, and we call them meta-heuristic. As an exercise, you find two physical problems that can be modeled as 1D unconstrained optimization, and you develop the model for those problems. That's all for this lecture. Thank you, and I'll see you in next class.